start the start of a series of talks I will give about the the generalized functions. Yeah, it is a very important topic in both mathematics and physics and engineering, etc. Okay, so start with a heaviside function. Okay, a heaviside function is a very simple function that takes the value 0 when x smaller than 0 and it's bigger than 0 when x equals to 1, h equals to 1 when is bigger than 0. It has a jump discontinuity at x equals to 0, so it's called a step function. So curious about what we are curious about is that why is it the derivative of the hx is this seems to be a strange problem because it cannot be differentiated at a point where x is 0 in traditional definition of derivative. But it can be a method to write about to talk about the derivative of this kind of functions, and its derivative can be written as a so-called generalized function, such as Dirac delta function. Yeah, the Dirac delta function is very useful in physics and is first proposed by the physicist Paul Dirac. But it is actually very useful in although Paul Dirac is uh, is famous for his dedication, his contribution of the quantum mechanics and quantum field theory. However, it is actually very useful in classical physics, such as electromagnetic theory, to use the Dirac delta function. So we will talk about a little of Dirac delta function, which is very interesting to see at first. Traditionally, we will teach this kind of so-called function. This function should be a quote because it's not a real function in traditional sense, but it is actually a somewhat generation of a traditional function, which is called a generalized function. It can often be told a function takes a value of infinity when x equals to 0, and which can be written as delta x. So in traditional electromagnetics, we have a point charge. The point charge is uh, can be written as this, and if we write the electric density, okay, electric charge density, we can write it as delta x, which equals delta x at the two symbols are defined to be the same. So we can write this or this to denote this kind of. So rho x, which equals the density of the electric charge, it has all the charges are concentrated in a single point, which centered a 0. So this should be written as delta x, delta y, and delta z. And if the x0 equals to x0, y0, z0, then we can write this as delta x minus x0 or delta x minus x0, delta y minus y0, times xz minus z0. Yeah. So a very classical problem of because this is called a potential, electric potential, which is defined to be the gradient of the phi is E, is the electric field. And also we have a Gaussian law of the electric charge, electric field, which is equals to enclosed. Okay. So here it equals to delta or Q delta. Q is the charge of the electron or proton or any particles that have a charge, but it is a point particle. So it can be like this with x minus x0 if this is a point charge centered at 0. Okay. So let's talk about a special case of this kind of point particle. We suppose we live in a one-dimensional world, and electric charge can be just written as a so-called delta function. So when in R1, the electric charge is delta x minus x0. That's it. Okay. So Dirac used this kind of so-called function, generalized function, when dealing with the problems in quantum mechanics. However, when in classical physics, we have already used this kind of notation. Yeah. So we can see that if electric charge is posed at x equals to 0, okay, we want to denote this function f equals to the total charge from x 1 smaller than 0 to x, then we can write x1 here. So from here to any x, write the total electric charge here. And we can know the function can be written as the Heaviside delta function. Okay, so this is 0, this is 1, this is 0, and when for all x bigger than 0, bigger than 1, hx takes takes 1. So fx equals hx, which was the definition is right in here. Or you can call it a unit step function. Yeah, we have some kind of properties of this kind of Heaviside function. You can see that Heaviside function is a very ordinary function, but it's not really continuous. However, it is still a very normal function, unlike the Dirac function we talked before. So, why is this kind of thing? This can easily prove this to these two formulas. It's very easy. However, they are very interesting. There are many interesting formulas of Heaviside function, and we can see that Heaviside function can be written as this part, and this is hx. Okay, so y is h minus x is reflected through the y-axis, so this such as here. So this must be equal to some kind of infinity. You can see this is a constant function minus 1 when x bigger than 0. So this is a hx 1 minus hx. Yeah. So this is the left hand side of the formula 2. And y is h a minus x Yeah. So bring a minus x into here. So we can see h x minus a equals e equals 1 minus h x minus a. Okay. So this is actually the same formula. We should discuss it more. We have very good properties. Okay, let's talk about the next equation. Okay, the next equation, y is h ax plus b. Yeah, so you can see h ax plus b can be written as h a x plus yeah, b quotient by a. Okay, a divided by a. So you can rewrite this kind of thing. And it's right diagonal of this. This is h. Okay, x. And this is h x. And this can be written as x minus negative b divided by a. So this is 0. This is minus b divided by. So this is so you can see hx is actually equals to hx. So this is equal to x plus b divided by yeah. It is true where seems to be true, but however, this should be work when a equals to 0. Mm, b equals to 0. I don't know where it's u and ux plus b equals to 0. And if yeah, if a is bigger than 0, if x is big, if a is bigger than 0, is like we can use this if a is smaller than 0. Yeah, this function is oh, yeah. So what if a is smaller than 0? Minus if a is bigger than 0, hx equals to hx. However, if hx equals to 0, it will become a reflection. So it will become at least. So this is h a. Yeah. So when x bigger than this, we can write this n plus when n equals to 0. Actually, another kind. So let's see. So if a is smaller than 0, h ax plus b equals h a minus x minus yeah. So this is can be changed to 1. So h is minus x minus b. Yeah. So we write this times h minus a. When a bigger than 0, this is 1 and this is 0. And vice versa. So we plus 1 and 2 equals h x plus b. No matter a is bigger than 0 or a is smaller than 0. Okay. We will talk about more in the next lecture.